Hello and good evening. So now I'm going to start to explain how I do this project. So in the first step, English of the line. First step now for the basic packages. I'm importing the basic packages. So NumPy ఒకటి కావాలి, pandas ఒకటి కావాలి, and all the required packages have been imported. So it's the first step. So in the next step, the data set has been loaded. It's the default of credit cards client.csv. The dataset has been read through pandas.read csv, and then just for understanding how the dataset is, to perform the most basic dataset and exploratory dataset analysis, I perform the head. So now 5 rows and 5 entries కనిపిస్తాయి. This is the most basic one, and then I'm trying to see the shape of the dataset so I can know how the dataset is in the how it actually looks like. 30,000 rows and 25 columns is the actual dataset. And now here ikkada em chestunante, now because the final column is what is a value to be predicted, I'm removing that and storing it in a variable called x, y, and the x contains all the remaining variables to be predicted. So it's just like using the iloc function to dynamically allocate the actual values that are needed for the model to be trained, and the actual class label which is need to be predicted in another variable. ఎందుకంటే మనకు అది మోడల్ ఉండదు, that is the one to be predicted. So I'm once again printing the shapes. 30,000 columns and 30,000 rows, 24 columns and 30,000 rows is, and just one big column of 30,000 rows. So that is a y, the class label which is to be predicted. And right now I'm doing the train test split. So I'm splitting the data set into 70-30 ratio. So since I have 30,000 rows, it would be 21,000 train data and 9,000 as test data with random state 0. I'll talk about this later. And I'm doing the standard scaling. The standard scaling is basically called as the column standardization, where the mean is set to 0 and the standard deviation is set to 1. The variation is set to 1, I believe so. So the data is column standardized, so the outliers and all the unrequired stuff will be removed. And now once again just printing the shapes of the data split. As you can see, 20,000 by 9,000, it's split into 75-25%, something like that, 70-30 ratio. And now I'm fitting this random forest classifier model with 2,000 trees. The n estimator actually shows the number of trees I need to I want to build in order to classify the next label. And this is a random state, is actually a seed value, which will be further explained here. Like you see, the problem of learning an optimal decision tree is going to be NP complete. This means the practical decision tree algorithms which are based on the greedy algorithm are based on the predictions made at each node. So such algorithms cannot guarantee to return the globally optimized decision tree. So when we run this model, this is basically pointless, since the globally optimized model does not exist with this kind of algorithms. This can be mitigated by training the multiple trees in an Ansible learner. So that's what we're practically doing. But when you see when building a large number of trees, this can be highly problematic. So in order to build a generalized tree, a globally optimized decision tree, so we're setting we're using a random state parameter to control the random choices made at each node of the decision tree building algorithm. since the random forest is basically a collection of decision trees, so this is basically going to repeat the n estimators number of times, because n estimators is the number of times we need, number of trees we need to be built actually. So random forest, this will be used in any case. The thing is, any value is set to it, it doesn't actually influence it, but the reason why we pass is is if we pass this random state, then each and every time we'll get the same result. So what we do is we make the the output kind of consistent with every time we try to build a model. So it's like we're doing an impossible task of building a globally optimized decision tree. So we're trying to sub-optimize that sub-part algorithm. So in this step we're actually trying to find out the feature importances, and we're doing reverse equals to true, means we're actually trying to reverse it. So we can so we get in the descending order of hierarchy of importance. So you can see is 92% importance and 70% importance and 56% importance. So it actually tells you how important each feature is. So we're actually doing it in reverse orders. So we are using the matplotlib.pyplot. Matplotlib, we're actually plotting a graph, so we can visualize how different this how different are the feature importances from each other. So with this we can know that the base 0 is more important and this gender is basically not very important. Means basically dropping this wouldn't cost us much. So now we're actually measuring or testing our model by using the F-score, the recall classification reports, and we're using the pickle to save the model, because we need this model in another application. We need this model, so we're trying to save this. We're using iter tools to get the combinations, and we're using the confusion matrix, we'll see later on. And the ROC curve is receiver operating characteristic curve. So it actually a graphical plot that illustrates the diagnostic ability of binary classifier systems, like the one that we've just been designing, as its discrimination threshold is varied. So when its classification level is varying, that's how it's being reported. So we imported all these packages for all that, and now we are trying to predict. We're actually performing the predict function on the test data that we previously split, and now we are printing the ROC under AUC, the AUC score, which is the area under curve score, which is supposed to be 65%. So we got 65% of area under the curve that we actually fit using the random forest model. And here we're actually printing the classification report, so we can know the F1 score and the recall in target with the precision and the support we've given with each value. So it gives the non-default, the zeros, the persons who are regularly paying the bill versus the persons not regularly paying the bill, and the macro averages and the weighted average of all the class labels here. And now we're building the confusion matrix. We're building the confusion matrix first, and then we are normalizing the confusion matrix, because the numbers here are 6,679, 381, 1229. So this is kind of difficult for us to actually understand. So we're actually normalizing it here with normalize equals to true, so we can get a completely normalized confusion matrix, which helps us understand because it puts it in a scale of 0 to 1. So as you can see, it's 0.1 to 0.9. All the values fit here between 0 to 1. And now we are actually printing the training accuracy, which is 1%. And we can get the test accuracy of this model by just switching this to x underscore train, x underscore test, y underscore test. We'll get the test accuracy. We need both to see how the model is actually fitable, how the model is actually trainable versus the actual model's accuracy value. And from here we are actually trying to do the neural networks version of the same thing. So here we are once again trying to normalize the data. We are column standardizing the data to fit it perfectly into the model, because what we're doing is neural networks. So for neural networks we're using Keras, and we're using sequential and dense. These are actually the methods of adding layers into the neural networks. So here we're starting a neural network. The sequential function actually designs a neural network, and we are adding 30 units of the initial input layer, input dimension being 24, and we have 30 nodes in the actual first input layer. And the activation function is ReLU, which is basically a rectified linear unit activation function. So as you can see, it is one of the most used activation functions in the world right now. ReLU is half rectified. So f of z is 0 when z is less than 0, and f of z is greater than or equal to 0 when is above or equal to 0. So whenever z is negative, it is f of z is 0, and when it is equals to 0 or positive, it is equals to z. So this actually is activation function that helps us in achieving weights and handle the transmission of data between the nodes. And here we are adding another 20 nodes as a hidden layer to the first input layer. And the next what we're doing is adding 2 nodes to the output layer, and this time the activation function is softmax. So the softmax is actually a simplified version of the sigmoid function. So sigmoid function actually tells you, it's a mathematical way of saying a range of real numbers and returns output value which falls in a range of 0 to 1. But here the softmax is actually different. So softmax actually calculates the probability distributions, and it will calculate the probabilities of each target class over all possible target classes, and this will always range between 0 to 1, and sum of all will always be 1. So here as you can see are the properties. The calculated probabilities will range from 0 to 1, and sum of all probabilities will always equals to 1. And we're using that as softmax because we need to find the probabilities of a person being defaulting. And now we're actually printing the summary here, which will show you that we're adding the 30 layers as input, 20 as a hidden layer, and then 2 layers as output. And all these are dense because they handle the dense data. And because the parameter number has been given here because it's a part of the neural networks. And then we're using the Adam optimizer and categorical cross entropy, because as you can see here, Adam optimizer is as an optimizer used in neural machine learning. That is a very different thing than the standard stochastic descent. It's actually an amalgamation of 2 different algorithms: adaptive gradient descent and root mean square propagation. So this actually maintains a per parameter learning rate and improves performance on problems with sparse gradients, adaptable gradient learning. And root mean square also maintains a per parameter learning and that are adapted based on the average of recent magnitudes. The algorithm does well on, you know, noisy data, or if you have got a clean data or noisy. So it's basically we trying to fit the data, we try to generalize the optimizer. We're trying to generalize on the data which we're trying to train in order to get the best accuracy. So we're using the Adam optimizer because it includes both of the algorithms, and both algorithm proves that it's it's quite effective when you think of it, because to show the convergent means of the expectation theoretical analysis. When you see that, when you see the graph, it shows that the atom is actually giving you less errors compared, the less loss functionality. Compared to it, we're using the cross entropy, because the cross entropy loss, the categorical cross entropy, actually measures the performance of a classifier model whose output is a probability value between 0 and 1. Exactly what we're trying to do now, because it's a probability value, it falls between 0 and 1. And cross entropy increases as a predicted value diverges from actual label. So when we're trying to predict, if the value is far different from what it actually is, the cross entropy value increases. So it actually shows you how well your model is when you're trying to build something different. So that's why we use it. And the metrics is accuracy. We want to know how accurate the fitting has been. So we're trying to run 100 epochs, and we're trying to shuffle the data between each of the run. As you can see here, it has run for 100 times. Each time the loss has been reported to be around 30%, while accuracy has always been around 80% of the time. So it actually shows the performance of the model in the initial stages when it's trying to build fit. And now we're here calculating the model loss and model accuracy. We're using the function model evaluate to test the model, and we're printing the model loss, model accuracy. This is the values we get from the model.evaluate. So we're just printing that, and we can see the model loss is 46%, while 46% of the times it was mistakenly, it was wrongly predicting, while the model accuracy is being 0.80% of the time it's being. And we're printing the ROC score again, the ROC AUC score, the receiver operational characteristic, and area underscore curve scores, because that's one of the more important things to us. And here we're printing once again the classification report and the confusion matrix. As you can see, with the normalized confusion matrix, it is practically the same thing we've done with the original the random forest thing. We're just trying to do it with the neural networks. And right here in the last and the final step, what we're doing here is we're trying to print the ROC curve to see how different each model, one model is different from the other. So right now we're here, so we're actually fitting the values here, the thresholds, the RF threshold and the ROC threshold, and these are the false positives and the true positive counts. And then we are plotting it by naming it random forest, and giving the area as ROC AUC, the area under the curve. So we are actually fitting it with area under the curve as the given area, and then we are similarly plotting the ROC curve for neural networks. And then we're plotting the base rate here, because we need to find out the actual the base value of ideas with which we compare. So this is the value against which the both models will be evaluated against, compare for their accuracy levels. And here we're putting the labels as false positive, true positive against the axis, and then the ROC curve as the label, and the legend here we've put it over here. So this is the area under the curve values. As you can see, neural networks has a area under curve of 49%, or it has of 65. So it actually shows that the deep learning models have still a long way to go when compared to this kind of models where it's simply a matter problem of classification. So it's recommended not to use two deep learning models in problems like these, since these models do not actually learn too much because the potential remains untapped. With this, I'm ending this, and I'm going to start the next in a few.